Hi, everybody. So, good morning, good afternoon, or good night for those who are really late. Thank you very much for attending to this webinar. This is the second webinar we are doing about vision. We did a session back in November. At that time, we focused more on how AI is augmenting the capabilities of robots, putting together vision and AI. Today, I would like to do a broader intro to vision, and later on talking about some specific cases. Let's go ahead then. So as Luis I'm Global Product Manager for Robotics Vision. So as a brief background of myself, I started in ABB some 20 years ago. During this time, I have covered several positions and roles, most of the time in the automotive business, working in sales, working in projects for a while, working in product management, but also in customer service. So I can say that I have a background, an open background, and I have covered several positions. Since 2019, before COVID, I took over the responsibility of being product manager for Vision, uh, and that was a great opportunity. And it was at the right time because since some years ago we were seeing that Vision was taking more importance in robotics. So I think that it's the right time for being in the right place. So as commented, so I will do on today's webinar, I will do a brief introduction on robotics vision. There's a lot of noise when we are talking about robotics vision, so let's try to put a meaning to the different type of words, of buzzwords that we are hearing. Secondly, I will comment, or we will go a little bit deeper on beam picking and item picking applications. Again, sometimes it's difficult to differentiate if we are talking about beam picking or item picking, which are the main difference between these two applications. Finally, of course, I'm working on ABB, Global Product Manager for Vision. I will introduce the ABB's offering related to Vision. And if I'm on time, I would like to have some 15 minutes for Q&A. So while I'm talking, you can use the room chat to post your question, or if not, by the end of the meeting, we could have this Q&A. So let's go ahead then. Okay, so as commented before, when we're talking about vision, there are many buzzwords. So we are talking about 3D, 2D, vision-guided robots. Then we are mixing all that with machine learning, machine vision. We are also putting neural networks. We are putting pattern matching, cloud filtering, vision sensors, pose estimation. So there's a lot of words that are coming on the field. So I'm pretty sure that you have heard a lot about them, and sometimes that's confusing. I remember when I started many years ago working on vision that I was having some difficulties in understanding uh, these words and the meaning of each of them. Big background before starting to the buzzwords. So it's why using vision in robotics today. So a simple uh, a simple sentence is that thanks to vision, robots can do more advanced tasks and they can boost their performance. Thanks to vision, robots are not essentially blind and we can perform more complex tasks. The combination of vision and AI, by the way, is changing the way that robots are interacting with their environment. So we are not limited to pick and drop from fixed positions. We are not limited on being or on the must of using complex fixtures. So we can have more variability on the environment, but also we can help the robot understanding what is the surrounding in terms of safety, or to understand which is the correct position to pick and drop an object. Also, we have to say that vision cost has gone down as well as performance has gone up. So we are in the right point. So we are reducing cost, we are augmenting, we're increasing the performance of the vision-based systems. There's a number that I'm repeating in most of my presentations, even if it's not a webinar, but it's also talking to customers, is that by 2025, it's expected that around 30% of the robots will be equipped with a kind of sensor. This sensor could be 3D, could be 2D, could be 15 megapixel, but could be 1 megapixel. So somehow uh, we are making standard the use of vision in most of the both applications. Okay, so going back to the buzzwords, going back to the meaning of vision. Okay, so this could be the tree of vision. So everything starts, I would say, with signal processing. Okay, signal processing at the end of the day involves the processing of electronic signals to clean them up, to extract information, or to prepare them uh, for a later processing or activity. Okay, that's signal processing. We are talking on the electronic signals world still. Then we go down, we go deeper to the vision side. We go to image processing, and then we are talking about all the techniques that are primarily used to improve the quality of an image, to convert this image to another format, or to change it, or to change this image for later work. So from signal, from the electronic signal to the image, we are already in the field of vision. Then we move laterally to computer vision, which is about extracting information about this image that it has been provided before. So we capture the information, we transform this information into image, and we clean it up, and then we understand what this image is telling us. Before, we have been talking about machine learning, this new science that it's in fashion and everybody's talking about that. Let me say that machine vision is a super valuable tool to improve a number of processes, but at the end, it's a tool. By itself only, machine vision is nothing. At the end, it's a number of statistical tools, but it's super valuable when we are putting together for an objective. And at the end, machine learning is the branch of the family which is focused on recognizing patterns in data. This is what we are using mainly in computer vision. We can say that we are still in the scientific domain. So we are working still with signal. We are working on the theoretical world. When we are going down to the engineering domain, when we are going down to the application, is where we find machine vision. And machine vision at the end refers to the industrial use of vision for automatic inspection, for guiding, or for process control. And then if we go to the realm, to the world of robots, that means when we are combining machine vision with robots, for instance, we are combining these vision algorithms with kinematics, with motion control. So when we are putting the vision to a specific application, that's when we are really seeing the potential of the vision and when we are arriving to robot vision. We have not to forget optics, which is also on the base. So we are mixing electronic signals with the optics, which is a physical study. And then we are arriving to the end. So this is more or less the product tree, or the vision tree. And that's not myself who was writing on this way. There's here on the screen, we have a blog that it was written some time ago. And I think that it was a good introduction to understand these buzzwords, okay? Signal processing, image processing, computer vision, when we are starting to understand what the signal is telling us, machine vision, when we are extracting and when we are working already on the inspection, guidance, or process control. And then when we're mixing that with the robot capabilities, it's when we are talking about robot vision. Okay. Let's move on then. We have been talking about robot vision. The natural step is going to the type of applications that we can do with robots. Okay. So typically, many authors are dividing in different ways, but myself, I like dividing into these three uh, column, these three type of applications. Number one, we could say it's robot guidance. At the end, we could say that it's the natural when we are talking about robot vision. In this sense, we are using we are using cameras and sensors to provide information to the robot on size, shape, location of specific objects. And this information is essential for manipulation and for assembly. We are talking about applications like item picking, bin picking, depalletizing, or assembly guidance, or screw driving, or pick and place. So I would say that around 60 to 70% of the applications that we are doing with vision and robots are in the robot guidance field. Secondly, there's another type of applications, which is quality inspection. I would say that in some cases, or in most of the cases, the robot is a carrier of a vision system, which is providing information about the quality or how an object has been assembled, by the way. We have applications like assembly inspection, geometrical analysis, or cosmetic or defect detection. I was saying that a robot is a carrier. That doesn't mean that the robot is dumb, because in some cases we need to put this sensor to a very specific position, or we need to change the point of view of the sensor to create uh, a complete view of the objects. So this is quite popular in geometry inspection, in assembly inspection, or in cosmetic, as I said before. Third column related to navigation and mapping. We could say that that's typical from HGVs, but also we have not to forget that nowadays we're using sensors for safety purpose. So human machine safety, that could apply to HGVs, but also it could apply to robots. So making the robot understand the environment. There is a number of companies using time of flight sensors around an industrial robot to map the environment, to know if someone is going inside the working envelope of the robot, to avoid collisions and to prevent for having some accidents. At the same time, we have the typical application with vision sensors equipped to AGV or to a moving robot, where the robot is adapting its path depending on the obstacles that it's finding. And at the end, that's a decision making. So we are combining the feedback from the sensor to AI in some cases. So let me take out the music. So before I was talking about the session that we're doing back in November. At that time, I was explaining in detail these three columns. I was explaining in more detail even how AI is used for this type of applications. It doesn't mean that all applications related have to work with AI, but it's a way to increase its performance. Let's go ahead. Okay, so today, once we have defined vision, I would like to talk about bin picking and item picking, as I said. So on the family of picking applications, we have, again, a rainbow of applications. And again, there's a rainbow of technologies that could be used for doing the picking, the object picking. Depending on, I put it on the x-axis, let's say the application complexity, and on the vertical axis, the variability, and that means how the items are arranged, if they are the same items, if they are different items, which is its position. We can see that the first one in complexity, or the simplest one in complexity, but also in variability, is 2D part picking. So at the end, we can solve that with simple 2D sensors using a traditional vision approach. Going up on complexity and on variability, we have semi-structured bin picking. In this case, in semi-structured bin picking, we are always picking the same type of part, but I was talking about increased complexity compared to a previous one, because the position is not fixed, despite they are put it one on top of the other, more or less, but there could be some variance in the positioning. So we are not having fixed positions. In this case, again, we are using a traditional vision approach, which is 2D CAD matching. That could be augmented or can be improved by using AI. In fact, there are some companies using stereo vision and AI for this type of applications, as well as for unstructured bin picking. So in this case, an structure bin picking, we are again picking known objects, but they are chaotically arranged in a bin, in a tote. Okay, but always talking about one single item. We can use the traditional approach, CAD matching, or we can use also CAD matching plus AI to improve the performance of the system. And then we have, when we are going we are increasing the complexity and also the variability, we could have the application of the palletizing that I was talking on back in November. So we have different type of boxes, uh, chaotically arranged inside a pallet, of course, but chaotically arranged. So you never know what the robot will pick next or what the next pallet will bring. Okay, so we need to mix vision tools, traditional vision tools with AI. And finally, we have random item picking, which I'd say that it's chaotically in arrangement of the objects and chaotical in the variability of objects. So you can have a big variety of objects. Okay. Bin picking and item picking. So I will focus. We have been talking about some 5 different applications, but I will go to these 2 because for me they are the most interesting today. And on top of that, there's a number of companies that are providing solutions for these challenges, which nowadays are not so challenging. On the bin picking side, we are talking about picking of known objects, which are randomly arranged on a bin. Typically, we are talking about machine parts, casted parts, billet, plastic components, or other type of parts used in assembly applications. The traditional segments are machine tending for manufacturing, like metal, plastic, etc. There's a long number of segments where this bin picking can be used. When we go to the other side, to item picking, we have unknown objects which are randomly arranged from a tote, from a bin, from a bulk. And we are talking about soft deformable objects, transparent, reflective objects, small thin objects, and complex patterns or backgrounds. And typical segments are e-commerce, pharma, parcel, manufacturing related to order picking. Before going more on detail, maybe this slide should be before, but I think that has sense doing a small introduction and then going back. In this case, the different use cases. So we have how the complexity or how the use of the technology is growing with the complexity. So on the initial use case that I was commenting, we are using 2D isolated. At the end here, we're using standard or simple 2D tools and 2D cameras. So it's easy to program. It has fast runtime because the processing time is really short. And we are talking about low robustness because if the parts are stacked one on top of the other or there's occlusion, so we cannot pick these parts. We have the structure 2.5 structure bin picking. So at the end we have piles, but we are picking 3D objects that these piles could be tilted, could be moving, could be not 100% in a good position. So we are using in this case 2D point cloud matching. Also, again, short training time, slow runtime because we are starting to need more processing time, more processing capability, sorry. Low robustness, again, if we are having some deviations, if the pile is not properly arranged, we could have some difficulties. Moving to random known objects. So we could say that it has moderate training. I will explain later on how we are doing this training. We have moderate runtime, increasing little by little the computing needs. High accuracy in case of using expensive or high accuracy point cloud cameras, and moderate robustness depending on how we are picking the objects, which is the algorithms that we are doing, or in case that we are using AI in some cases. And third, random objects or item picking. So we have 3D tools plus AI. In this case, we need a long training time because we need to do a neural network training and AI training, which some thousands of samples. Sometimes we can have less than thousands modifying the image that we are taking. We have moderate accuracy because we are not, since we don't know which object we will take, will pick next, we are just providing the robot pickable surfaces or pickable points, so we don't know exactly how we are picking. And finally, if we want to have high accuracy, we should need a kind of textureless, or we should need a kind of cut matching. Okay, so couple of nice videos to reflect or to explain what we are talking about. In this case, it's an example of a beam picking application, which was tested in our machine tending global solution center in Jönköping. At the end, this part we could say that it's complex on the shape. You can see that it has a lot of corners. It's difficult, but it's simple because it's not reflective. At the end, this could be casted part, and you are not having the impact of reflection. I will explain later on how we are doing the training. I will not go in detail because I understand that there's different the previous know-how from the team or the audience is broad. And then item picking, and in this case, we are seeing some samples. This was done by our team in US. We are picking boxes, bottles, and tubes. In this case, toys, which is a nice example because toys are completely different one to the other. It's completely random shape. Blisters and clamshells. It's difficult item sometimes to pick because there's carton, there's plastic. Bags and pouches. In this case, also in apparel that we'll see next. The complexity, I would say that it's also on how we are picking, on the type of suction cup that we are using. And then when we are putting all together, just to show the capabilities of the system. On one side, on the beam picking, we are not having AI in this example that I'm showing. On the other hand, on item picking, AI was a must to be able to pick these randomized objects. Okay, until now, so we have this classification, beam picking, item picking. On beam picking, we have known objects, while in item picking, it's completely unknown objects. The vision sensors that we are using are 2.5D or 3D, or maybe also 2D stereo cams using two 2D cams. At the end is like having a 3D. Exactly the same in item picking, where in most of the cases we are using 3D cameras, but also we can go for 2D stereo cams. On the object pose, so in beam picking we have semi-oriented or random, while in item picking in most of the cases it's completely random. On the vision approach, we have classic point cloud matching or the use of AI in some cases for beam picking. In item picking, it's always going 3D plus AI. The training, which is missing, and in the case of beam picking, it's CAD-based training. At the end, we are uploading the CAD model, or some vendors, they are providing the capabilities to scan a part and creating a CAD model from the real part. In item picking, by the way, which is missing here, it's training of machine learning. We need to train with some thousand parts or augmenting the data that we are having just by tilting, changing contrast. So we'll comment that later on. Applications, mainly machine tending for beam picking and order picking for the item picking. Use cases, as commented before, metal versus completely random objects. Supported gripper, and that's something that we have not commented before, but in beam picking, we have, in most of the cases, fingered grippers. Some cases also we can use suction cups or even magnetic grippers. On item picking, in most of the cases, we are using suction cups, but also sometimes we are using a combination of suction cups and grippers. We'll see later on. And on the picking point definition, it's also good to mention that in beam picking, we are defining the different pick strategy, or the different picking ways for this known part, while in item picking, since we don't know the objects, there's an auto generation of picking points based on machine learning. The scope of supply in this case, so that's a standard cell which is supplied by our team in machine tending, our team in Sweden. This standard cell, at the end of the day, it has the same components as for item picking or for bin picking. We have the vision scanners, so I put it here some examples. We can have one of them, it's a Framos based on Intel sensor. We have a camera from a sensor from Photoneo, 3D sensor, and also we have a high-end sensor from Keyence. The selection of the sensor will depend on the layout, depending on the height, that the available height. That will depend on the field of view. That will depend on the accuracy which is needed for picking the objects. That will depend on the light conditions. So at the end, there's a big number of things to be considered when we are selecting a scanner, a 3D vision scanner. Exactly the same if we are using 2D stereo vision. Then when we are going to the application gripper, we have plenty of manufacturers which are doing a great job on the design of and manufacturing of grippers. Here we have some samples by Schunk, if I'm not wrong, which are the finger grippers. Depending on the type of objects, we can select one or the other. And then some examples of Payap and Schmalz. One is kind of soft fingers for picking objects. In some cases, it is used for foot and bed, but also to random objects, while the suction cup is commonly used in order picking, in post and parcel, you name it. Afterwards, so we have the vision scanner. The signal is arriving to the vision controller. In this case, we are doing the interpretation. We are understanding the information that we have from the vision scanner, and then we are using machine learning to provide the output and to provide the picking point to the robot. Okay, so this is a typical scope of supply for item picking or bin picking modules. I don't want to repeat on the cat matching, AI bias detection, and so on and so forth, but that's the typical path that we are doing for the problem solving. So we detect, thanks to vision, the object. We understand the pose of this object inside the tote or the bin. Then we need to plan how to grasp this object and to define the picking points. This is still on the vision side, I would say. We are going then to a robot problem, which is the motion planner, how to plan the peak motion without forgetting that we need to create a collision-free planning in order not to have collision with the bin when we are taking out the component. And then we have the robot executing the pick. It's going, picking the object, and then there's an afterwards action, which is the dropping. So we can have a drop in another tote, we can drop in a container, we can drop in a chute, or we can go for a more precise placement. For instance, if we are doing classification with the help of a barcode reader, we can do classification and putting in a specific container, in a specific tote. Also, we can go to precise placement. In that case, we need a secondary camera to understand which is the situation of the destination bin. But that's out of what we are going to talk today. But there's a number of after peak actions that could be done. I commented before on the training. So on the bin picking side, the training, it's quite simple, I would say. So first of all, we need to upload the CAD model of the part that we are going to pick. As said before, in bin picking, we know the part, so we need to upload the CAD model. If we are not having this CAD model, which is the case in some circumstances, we can use the software, you can use the vision to create this CAD model. Then this is chicken and egg, the next one. So we define the gripping points of the object. Once defined the gripping point, we define and design the gripper. So that's chicken and egg, as I said, because we can first define the gripper and then try to find the best strategy to pick, or we can design the gripper depending on the picking points. So that will depend on the case. Then we need to introduce into the simulation tool the layout to calculate the trajectory, and then creating a collision-free path. Kiens, Photoneo, other suppliers, they are having all of them simulation tools, like this one we have here. Let's see. Up. This is not going. Okay. Wait a second. That's moving. Yes. So here you will see we are creating that's a simulation. So we have, in this case, that's brake discs. You can see that in purple, you have the trajectories that in thin lines in purple, the trajectories that the robot is doing. And with that, we can completely simulate and program the trajectory of the robot for emptying the bin. Okay, it's quite simple, as I said, loading the model, defining the ripping points, defining the ripper, layout. In this case, it's the position of the robot and the position and height of the bin, and then the creation of this collision-free path, which is at the end the output for the execution of the robot. Next one, again on the training. So before it was just uploading a CAD model for the part, uploading also a CAD model for the gripper or designing the gripper. When we're talking about random item picking, different objects, we need to train the vision system with a large number of data. In this case, and that's a real case, so we have a toad with a number of objects, and we are taking images of these toads 1,000 times, n times, depending on the type of objects that we are taking. We are taking, in this case, pairs of image. One is the RGB, another one is the depth, which is giving information on the depth of the bin, where is the position and the set of the objects, and we are repeating this a number of times. Next is doing the labeling. Somehow it's classifying and making the robot understand what are the objects to pick. And in this case, you can see that we have in light red, this is the pickable area, and the surrounding in strong in red, this is the area that it's excluded for picking. If we're picking an object from the corner, it's easily that this object will fall down because it will bend. We are considering that we have some thin object in this case. So we are doing this labeling. So we are doing in a large number, n again, that could be 1,000, 100. If we are just having 100 samples, what we can do is play with rotation of the images. We can play with the contrast. We can play with different type of parameters to change how we are perceiving this data. Finally, we are selecting a model for the neural network, and we are doing testing. We are validating this neural network and then seeing if the output fits. If the output is fitting, great. If not, possibly we need to retrain. Possibly we need to change the neural network. At the end, the neural network is taking some inputs, converting into the expected results. So if this is not fitting, that might be because we are not providing a neural network which is fitting the application, or because we are not having the correct labels, or we are not having a correct number of samples. Okay. And at the end, the result is what you can see here. So we are picking boxes. In this case, this is randomly arranged different type of boxes. The other ones were white mainly. These ones are in color, also randomly arranged. They are one on top of the other, without prior information about the next items that will come in the tote. In this case, this is some healthcare components, I would say. They are in plastic bags. This is a blister. So we can see that the robot is quickly adapting to the next objects that are coming. Okay. Good. So going a little bit deeper without going in too much detail on the training. So what we are doing is starting by having what we call a global model, which is a model that would fit all applications, which is filled by data samples. This is we are doing the training process, as I explained before, and we have this global model. When we are going to a new project, when we're having a new use case, we are using initially this global model and running what we call supervised production. We are validating this model. If the model is okay, no problem. So we have this global model, which is working in a big number of cases because it's a global model based on many samples. If the model is not fitting, then we need to do data collection with the parts that we are running and improve this global model. At that time, this model will not be global anymore, but it will be a model for that specific customer. There's also a lot of discussions on sharing data. Who owns the data? That's a big topic when we are talking about machine learning. It's clear that data, in our case, belongs to the customer, and this data is used to improve the performance of its own process. Okay, so we are not sharing data from customer A to customer B. Okay, so big intro. I'm arriving to that time, but big intro on Vim picking and item picking. We talked briefly about how machine learning is enabling us to pick random objects. We have been talking about Vim picking and how we are training CAD models. And then we go to the ABB's offering. So we have the platform. So this is a division that I think that it's simple to understand. What we call platform products at the end of the day are it's integrated vision, which is a 2D vision toolbox. At the end, we are providing a set of 2D sensors, and we are providing together the tools to make possible a large number of applications. Okay, so this is a starting point. We can do 2D item picking, as we said at the very beginning, but also we can do pattern matching, we can do quality inspection, we can read characters or doing barcode reading. Platform product, many applications could be tackled. Also, second layer, we have the software products. So these products are more specific to or more related to a specific application. We have high-speed alignment, which was introduced by ABB last year. It's based on a technology called visual servoing. We are using a closed loop to increase the capacity of the robot. We have to think that thanks to high-speed alignment, we are able to do to reach 0.02 millimeters of accuracy on assembly applications. That's commonly used in electronics. Dynamic assembly pack, it's also using visual servoing technology, but in this case, it's to align the speed of a moving object with an object, with the robot application. So used in automotive for cockpit assembly, for placing an assembly of doors. And at the end, this is same technology, visual servoing, in one case for tiny objects, like putting the camera on the smartphone, or for large objects like in vehicles. Then we have what we call Path Tuning Master, which is a software tool to extract features from a part to guide on gluing or on welding applications. And then we have Pigmaster, and here I want to make a comment. Vision is a small component of Pigmaster because Pigmaster is a software package for packaging. At the end, Vision is just a small portion, but I don't want to forget this exceptional product. Then we go for application modules. We have Flex Loader Vision, which is developed by the machine tending team that I commented before. And of course, they are focused on machine tending, on picking and 2D picking, 2.5D picking, 3D beam picking for loading into machines. That could be CNCs, that could be stamping presses, that could be different type of machines. Robotic depalletizer, which was introduced last year, as I commented before, random boxes, randomly arranged boxes in pallets. Then we have 3D quality inline, which is a functional module, which consists mainly on a set of tools for quality inspection and digitalization. And then we have standard cells, which is the Omnibus 3QI, which is providing a complete cell, including the robot, the vision sensor, the vision computer, and also all the cell. And I will talk, since I have been talking about item picking and bin picking, a couple of examples that we have in ABB. This video is pretty nice. It shows a standard cell developed by the machine tending team. There's also the possibility of, instead of acquiring the complete cell, just acquiring the functional module. In this case, it's nice because we are seeing an AGV loading and unloading a machining cell. The robot is picking from a tote, and this is being picking. You will see that all the parts are exactly the same. You can see here that could be a layout of a small SME, which is working on machining, having different type of robot machines. You can see the scanning. In this case, we're using vacuum to pick the objects because they have flat surfaces. I don't want to forget that the machine tending team in Sweden, they are open for testing any type of objects. If you want to do bin picking, they are testing with different technologies and trying to find the best technology for the part. That could be highly reflective, brass, aluminum, steel parts. So they are doing these testings and defining the best solution, also designing the gripper. Definitely, that's a really nice setup. Up. Second is item picker. So in Pack Expo in Chicago, by the end of 2022, it was in November, we were there doing a preview of an item picker cell. At the end, ABB was showing here a functional module, including a 6-axis robot, the 3D vision sensor, the processing unit. The particularity here is that you can see that robot is picking from one tote. I will put it again, picking from one tote, doing the barcode scanning, and then classifying depending on the type of objects that it's picking. At the end, you can see here, this is a box. Afterwards, it's picking a kind of cylinder or a tube. Okay. In the coming months, we'll talk more about this item picking, and this preview will make a reality. And all of a sudden, we arrived to the end. So now we have time for questions. So I delivered what I promised. So we talked about vision. We talked a little bit about item picking and bin picking, and we're arriving to quarter to the end for questions and for clarifications. Luis, hello again.
Hello again, and thank you for a great presentation, Tony. It's been very nice listening to you, and I think we've all learned a lot. And as you mentioned, it is now time for the Q&A. So if you have any questions, please write them in the room chat. I've written a welcoming message there, so you can find it. Just write any questions you might have, and we will make sure that we answer them. So we have not gotten any questions yet. I can ask one of mine. I was a bit curious on, you mentioned that you're using neural networks as a machine learning algorithm. How deep of a network are we using in the products? Is this like super, the computing power needed since it's a neural network?
So
Is that
the
a problem?
basic component of a neural network is a perceptron, is a neuron.
Mhm.
So the more complex the task is, the more neurons, the more hidden layers that we need to have. Um, I don't know exactly how many layers we are using today in item picking application, but I can tell you that it's a complex task. So not in most of the cases, or in our case, we are using GPUs because we need high computing power. These GPUs are embedded in what we call the vision controller, the vision box. In future, why not? We could have these kind of accelerators or GPUs directly integrated in the rod controller, but this is not yet a fact. It could be nice having all this computing power inside the robot, but nowadays, in most of the cases, most of the applications, we are having uh, these GPUs in the vision box.
All right, thank you. We have another question, and I'll read it out loud. It is, does ABB offer services to help develop and prove out an application prior to purchase of vision products in North
Mhm.
America?
Okay, so it's a very nice question. So um, in North America, in Atlanta, there's a, a CSSR location, which stands for Consumer Service and Service Robotics. There's a really nice location. There's a really nice team. And for instance, for the palletizing or also for item picking applications, they are the contact point and they are having the capabilities to test the applications. We are talking in most of the cases of sending some samples, testing, seeing that we can pick the objects. In some other cases, we are also trying to get a commitment on cycle time because it depends on the criticality of the applications. I'd say that nowadays, especially in very critical applications, is recommended doing these testings. On the other hand, in Sweden, we have this team in Jönköping, which is a very nice location. This is for machine tending. They have, I'd say, 3-4 different systems with different sensors, mainly for beam picking. So if you want to test depalletizing, item picking, North America, it's perfect. Beam picking, I think that also some of our colleagues or my colleagues in Auburn Hills, they can support this application, but we have a testing lab in Sweden, which is really nice.
Thank you for that answer, and thank you for the question. You mentioned before some future ideas for vision. Can you mention something else regarding ABB's portfolio? Where can we implement machine vision?
Okay, so at the end, vision is growing quite a lot, and we are seeing more and more applications where vision can be used. So at the beginning, when I started in robotics, maybe we're using clamping system, we're using centering system, maybe a gravity table for centering the parts. Now this is replaced by vision, 2D, 3D vision. More and more we can see racking applications where we are using robots to pick the part out of a manufacturing, stamping, or welding line. This is also going into assembly, not only big assembly, but small part assembly for guiding uh, the assembly of different parts. Also on quality inspection, we are using that for geometry inspection, but also for cosmetic inspection. That means that when we are manufacturing body side, when we are manufacturing an automotive part, we don't want to receive the product with scratches, so we can check that. Nice thing also is that more and more for this geometry inspection, we can go for inline solutions because we are increasing the computing power, we're improving the algorithms, so cycle time is much lower. So we can check 100% of manufactured parts, not only statistical as it was before, but we can check quality of 100% of manufactured parts. Out of that is plenty of applications related to item picking, like could be put wall, like could be track and loading, uh, a number of applications related to assembly. So there's a big A rainbow, again, I love using rainbow when we are talking about many different possibilities, but there's a rainbow of possibilities for using vision.
Sounds great. Looking forward to hear more about that. We haven't gotten any more questions as of right now, so if you have any questions, please write them in the chat. And until we get another question, why don't we hand it back over to you again, Tony, to just give us some few key takeaways. What do we need to remember when walking out from this tech talk?
Okay. So I like explaining all these topics on vision. I think that these topics are helpful to clarify what we understand as vision, what can be do with vision. Number one is we were going through this family tree of vision, starting from signal processing until arriving to robot vision. At the end, we are combining machine vision with robots, and then this is robot vision. We can do a number of things combining the visual perception and the motion and the kinematics. That's what we understand about robotic vision. Secondly, on the picking applications, we have been talking from 2D simple applications to really complex applications which needs AI. That means that there's a number of tools. Not always 3D and AI is the solution. In some cases, going with a very cheap camera could be more than enough when we are talking about 2D. Some cases, we need more computing power, more capability for the vision sensor to develop our solution. So there's some work to be done on the system selection. Finally, I want also to talk about, one of the takeaways is that ABB should be the partner of choice when we are talking about vision-based application. We are doing a lot of effort in bringing more vision capability to the robot side and making vision, let's say, a standard for any type of robot application.